Here I'm showing you the kinematic diagram for an articulated manipulator, and we're going to do the inverse kinematics for this manipulator. We'll start here by looking at the top view. From the top view, my first joint just looks like a circle, and I see the X and Y axes pointing off to the right and up like this. Then the second joint is right on top of the first, and I'm going to draw this as if theta 1 is not equal to 0. So it kind of looks like this. This whole distance here is the Y position of the end effector. So I'll call it Y03. And this distance here is the X position of the end effector. These are our inputs in inverse kinematics. And this is theta 1. Now, besides being able to identify what different distances are, it can also be very helpful to you in doing inverse kinematics to be able to identify what distances are not. For example, this distance right here looks like it's the distance A2, but that's actually not true. The reason why this is not A2 is because the joint theta 2 might be rotated so that this link is pointing up towards us or down away from us. And what we're actually seeing is the projection of the link A2 on the XY plane. Since this distance is the projection of A2 on the XY plane, the distance from here to here is not actually A2. So likewise, it also appears that this distance here is A3, but that also is not true because the joint variable theta 3 might be rotated either towards us or away from us, and so this distance is actually the projection of the link A3 on the XY plane. At the moment, I don't really care what these distances are. If I need that later on, we'll go back and fill it in. But for now, the only joint variable I can see from the top view is theta 1. So we're going to write an equation from this view for theta 1, and we can get that from the tangent. So theta 1 is the inverse tangent of y over x, the xy position of the end effector. All right, now I'm going to scroll down a little bit and we're going to take a look at the side view. From the side, my first joint now just looks like a rectangle, and the second joint looks like a circle, and I'll draw theta 2 not in the 0 position and theta 3 not in the 0 position. Now, I have a couple of options for how I could draw this. I drew this manipulator in the elbow down position. We could have drawn it the other way around so that theta 3 was negative and the A3 link was pointing down in the elbow up configuration. And if we did that, our equations would come out a little bit differently. So in this example, I'm going to be showing you the elbow down configuration. So I have the z-axis pointing up here, and from the side view, that's the only axis I can pay attention to. This distance here is the z position of the end effector. Let's label a couple of other things that we know in this picture. This distance here is the link length A1. This distance here is the link length A2. And this distance is the link length A3. Now, it's important to note that this distance here is actually not the x position of the end effector. The reason for this is that we've already said that this length here is A2 and this length here is A3. But the joint theta 1 could be rotated in any angle. So it may not be that this arm is lined up with the x-axis. And that's why we can't say that this distance is the x distance. That's only true when theta 1 is 0. And we have to write these equations to be true no matter what the value of the joint variables are. So I can't call this x03. Now I need to label my joint variables. Here I can see theta 2, and then this angle over here is theta 3. It's important to note that theta 3 is not defined from the horizontal. So I didn't dash a horizontal line here and define theta 3 from that. Theta 3 is defined from an extension of A2. So this dashed line that I put here is extending the link A2, and theta 3 is defined as the angle between this extension of link A2 and the link A3. Okay, so the next thing I'm going to do is identify the triangles in this picture that are going to help me derive the inverse kinematics. And there are two triangles that are really useful to me. The first is a right triangle, which I'm drawing in purple here. And then the other triangle that's going to be really useful is this orange triangle. The ability to see which triangles are going to be useful to you is a skill that you'll develop with practice. But in general, it's true that almost always a right triangle that identifies the position of the end effector will be useful, and then a non-right triangle where one of its links or one of its sides is the same as the hypotenuse of the right triangle that you drew are almost always two triangles that are going to be useful to you. So that's why I picked this purple and orange triangle here. Now I'm going to label some of the angles and sides that will be useful in my derivation. This angle I'll call theta 1. This angle, which is a part of the purple triangle, I will call theta 2. And then I'll label one more angle in the orange triangle, this one right here, I will call phi 3. So I've got phi 1, phi 2, and phi 3 as new angles that I can now use in my derivation. Also, I'll call the two legs of this purple triangle R1 and R2. And the hypotenuse, which overlaps between the purple and the orange triangle, I'll call that one R3. So let's start by finding our two joint angles. Theta 2 will be phi 2 minus phi 1. So if I can find equations for phi 2 and phi 1, then I'll have theta 2. Let's start with phi 2, part of the purple triangle. That one is simply the inverse tangent of R2 over R1. So now I need to find equations for R2 and R1. Let's start with R2 because I think that's the easier one. R2 is the z position of the end effector minus the link length A1. To get R1, we have to look back up at the top view. This distance here is R1. R1 is the projection of the entire arm on the xy plane. So I can find it from the top view by using the Pythagorean theorem. I'll square root the squares of the x and y positions of the end effector. I'm going to start labeling my equations right away here so I know what order I have to put them in my code in order for this to work. So equation 1, I can do that one right away. Equation 2, I know everything on the right hand side of that equation. Then I already know everything on the right hand side of this equation, so that'll be 3. And then once I have R1 and R2, I can now do equation 4. Now I still need to get phi1 before I can get theta 2. So let's try and get phi1. Phi1 is an angle in the orange triangle, which is not a right triangle. So I'm going to use the law of cosines to get that. Okay, so I just used the law of cosines. Oh, and this is supposed to be phi1, not phi3. Let me fix that right away. Okay, and then I need to solve this equation for phi1. So I'm going to write it out solved for phi1. I subtract a2 squared from both sides, and I subtract r3 squared from both sides, and then I divide by negative 2a2r3, and then I take the inverse cosine of that whole equation. And I'm just writing out the result here. Okay, so let's call that equation 5. Oh, but that can't be 5 because I haven't yet found R3. Let's go back and put in an equation for R3. I can use the Pythagorean theorem to get R3. So we'll do that here, and then we'll call this equation 5. Okay, now that I have R3, I can do this as equation 6. And then now that I have phi1 and phi2, I can solve for theta 2 as equation 7. Now all I need is an equation for theta 3. Let's see if we can get an equation for theta 3. Theta 3 is equal to 180 minus phi 3. So I need an equation for phi 3, and phi 3 is an angle inside the non-right orange triangle, so I'll use the law of cosines. Almost always, when you're trying to find a part of a non-right triangle, you're going to use the law of cosines. Okay, and then I'll solve this equation for phi 3. And we'll give it a number so I don't forget what order I need to do these equations in. This is equation 8. And now that I have phi 3, I can do equation 9, solving for theta 3. And here we go, we're done. We have equations for all the joint variables, and everything else is known, so we're done.